3.511. What we have here is tangent. Okay. And your job is try to find y prime. All right. Chain rule. The first thing you do, secant square x minus y times the derivative of x minus y. On the right, you have a quotient rule. Derivative of the top, keep the bottom, minus derivative of the bottom, keep the top. Together, you realize y prime here, y prime here. Let's isolate them. Just y prime if you do x squared plus 1 divided by x plus 1 square, so technically. Move everything together without y prime and with y prime. Factor things out. Finally,
Go.
Oh, sorry. Yep.
Oh,
Keep going.
no, you're okay. Oh, why is the 1/1 plus x squared not squared in the denominator in the solution?
Hold on. It should be. You're talking about this term, right?
Yes.
Okay. That comes from here. Can I see this one itself has it? Yeah.
Oh, yeah. Would it be an invalid step to just multiply the whole thing by 1 plus x squared squared?
It will work, of course.
Okay.
Think about the final answer, right? If I want to really do something about this, I can multiply everything by 1 plus x squared. So this one become secant whatever plus 2xy, and then 1 plus x squared with 1 plus 1 plus x squared times something like that. It's almost like 3 over 7 times 2 times 2. It will work. Okay. And there's really no way to tell which one is easier. Each one has its advantage. So if you did multiply, it's totally fine. All right. Emma?
Can you do 3.4 number 10?
10. Oh. $47. Okay. Well, it's long. We just do quotient rule since it's 3.4. After that, I will do it in another way if we apply log. You can see log can help a lot here. But let's just do this. The derivative of the top minus keep the bottom minus the derivative of the bottom, keeping the top. (46) times 4y cubed plus 3. and then square the bottom. Sounds good? Okay, I would say you can keep it there as the answer. Certainly, these two can be simplified by canceling the term here, but more or less, yeah, it's just one step. I think it's okay if you just keep everything this way. Sounds good?
I think it's asking for G double prime. So would you do that one more time?
It's actually looking for G prime. So look carefully. The first prime probably come from the way they did G like that. Okay, it's not a prime.
Okay.
If you are looking for G prime, I definitely say, hey, go with log. This is ridiculous. Okay, so for log, not prime yet. Minus 47. 47. Okay, now you take the derivative. You have 1 over gy times g prime y equals 10, 1 over times 16 minus 47, 1 over okay, then g prime y, whatever we have here. Parentheses times gy, which is so that will be your answer. If you do log differentiation, I would say it's easier. It's less likely to make mistakes. Again, in exam, either way, if you do it, you get it correctly, I will give you the full credit. So it's really your preference. In general, if you have more than 2 multiplications or dividing, ln is usually better. All right. Adam, Zonic, do you still have questions?
No, you already answered it.
Cool then. All right. Any more questions? Let's move on to 3.9. And we were talking about related rates. We were talking about a snowball is melting. Okay. Then the volume is changing. Meanwhile, the radius is changing. Meanwhile, the mass is changing. Meanwhile, whatever it is changing, like the diameters are changing. Yeah, maybe I need another one. I use capital D. So for the same phenomena, a lot of things are changing at the same time. And then we feel like because they satisfy a certain kind of relationships, if I know one rate, I will be able to find all the other rates because all these rates are related. That's our goal. Now let's look at an example for a particular case. Let's say we have a snowball melting at, let me make sure I get the right number. It's melting at, where is it? Okay, 40 centimeter cube centimeters per second. Okay, so from here, you know it's talking about the volume because it's cube centimeter. Okay. Now the question is, how fast is the radius shrinking when the current radius is 4 centimeter. You have a snowball, it's shrinking for sure because it's melting. You know how fast it's melting in terms of volume. But what I'm asking is how fast it's shrinking in terms of radius. Sounds good? Number one, the radius is definitely shrinking. Number two, it's definitely not going to be 40. Number three, somehow, however, it should be related to how fast the volume is shrinking because volume and the radius has a relationship. Then their rate should also have relationships. That's my guess. Sounds good? Okay. Now let's see how to set this up. We want related rates. Basically, we need two rates. One rate we know, one rate we don't know. Okay? The rate we know, the shrinking rate of the volume, I will call it dV over dt. And that is going to be negative 40. Shrinking at 40 cube centimeters per second. What do I want? I want dr over dt. How fast the radius is shrinking? I know it's negative for sure. I know it's going to be centimeter per second, not cube centimeters. Okay. But I don't know the exact number so easily. Still okay? Cool. Then here's our job. Knowing dV over dt, find dr over dt. Usually, how do you do that? Well, this is how you do it. You take dV over dt, you set up an equation involving both dV over dt and dr over dt. Then you put everything you know, you solve for dr over dt. Sounds good? Okay, so you need an equation. Okay. The bad thing is, in general, we don't know the equation. It's kind of hard. Okay. Then instead, can you ask yourself, if I don't know the relation between dV over dt and dr over dt, do I at least know the relation between V and R? Not the rates, but just volume and radius, assuming it's a sphere. Do I know that? The answer is yes. That is coming from spherical volume formula. Sounds good? You want an equation between the rates, but you don't have it. Instead, you have the relation between the two quantities without the rate. The question becomes, can you go from here and somehow get an equation which has the rate inside? You just take the derivative on both sides by implicit differentiations. When you finish, you're going to have y prime, x prime, v prime, r prime, whatever prime, right? Then the equation start to involve the rates. That's how we do it. So take the derivative on both sides. This is already good. What's the derivative of 4/3 pi r cubed? That's going to be 3r squared. Sounds good? That's going to be 3r squared if you're taking the derivative with respect to r. But you're taking the derivative with respect to t, therefore times r prime. More precisely, r prime with respect to t by chain rule. This is dV over dt. So you start from here, you take the derivative, you end up with this. What technique did you use? Implicit differentiation, nothing more. No additional information. Sounds good? Do you have an equation between the rates now? dv over dt and dr over dt? The answer is yes. Now to solve it, I just need to put everything in order. Okay, what do you need? You need this is negative 50. Okay. For third state, pi state, 3 state, you need r squared. Luckily, the problem told you so. The current r is 4. So just put in 4. That is your dr over dt. Then what is dr over dt? That's going to be negative 40 divided by 64 pi, which is negative 5 over 8 pi. Finally, answering words. The radius is shrinking at, not this one. And particularly, I'm looking for the information of the unit. I'm looking for, can you tell the phenomena? Because it's shrinking. How do you know it's shrinking? Because dr over dt is negative. That means r is getting smaller, not bigger. Okay, if you end up having something positive, you're not going to say it's shrinking. You're going to say it's expanding or inflating. Okay. But for this case, it's shrinking. All right. Aaron?
And that's at a constant rate, right?
That's what?
That would be at a constant rate. It's shrinking at that constant
actually,
rate.
no, because this is the rate when your R is 4. When your R is 10, it's going to be a different rate.
Okay.
Right? So you can see actually it's not a constant rate. It's actually, how to say, if you think about it, if you really solve it, dr over dt equals dv over dt divided by 4 pi r squared. Do you see that? Okay, that means if you are melting at a constant volume rate, okay, then the shrinkage of your radius should be inversely proportional to your surface area. The bigger the R, the slower the shrinking rate of R, because basically you're trying to melt the whole thing outside, right? The bigger the sphere, the more thing you need to melt in order to get the same radius shrinking. But because you're melting at a constant volume, therefore you shrink less in radius when the sphere is big. Sounds good? Okay, so that's a very good question, by the way. We know this simply because we know R. And this only works when R equals 4. Once if you solve it, there's no R there, then you know it's a constant rate. For example, you can try it really quickly. And I think you can guess it. If your diameter shrinks at a constant rate, then the radius definitely shrinks at a constant rate, which is half the rate. Right? But for volume, it's not the case. All right. Nick?
How come when you take the derivative, the 4 over 3 pi just stays the same? Is that just a constant there or what?
How do you take the derivative of 3x squared? It's basically 3, and you take the derivative of x squared. Right?
Yeah.
So basically, if you have a constant, they come from the rule of CF prime equals C and then do F prime. So if you have a constant, just take it out. That's why this 3/4 just stay unchanged. And actually, 3/4 and the pi also stay unchanged. Pi looks weird, but it's still a constant. So it goes from here to here. Does it answer your question?
Yeah, that makes sense.
Cool then, yeah. Any other questions regarding this? All right. This is called related rates. Hopefully I show you a standard way of how to think about the problem, which we will write down. Also, I want you to solve your problem and write your steps in exactly the same way I just wrote, because it's clear, it's complete, okay? And I will state clearly my expectations. What is related rates? Okay. This would be what I'm looking for when you write down steps. Number one, you need to recognize this is related rates, which means you should identify two rates. One is the thing you want to know, and one is the thing you know. You know one rate, in this case, the volume. You want the other rate, in this case, the radius. Okay, so first step, state what you want and what you know, and show me that you know this is a related rates problem. Second, you need an equation to relate this to, which usually you don't have. So instead, what you should do is you first find an equation to relate A and B, and then you take the derivative to relate dA over dt and dB over dt. For example, do you know the changing rate between the volume and the radius? You don't. But you do know the relationship between the volume and the radius without the rate. So do that first. Then take the derivative to get the rate. Once you have that equation, solve for the rate you want from the rate you know. And when you finish, answer your question in words. This is essential, okay? I was asking how fast is the thing shrinking in terms of radius. Your answer should be the radius is shrinking at whichever rate. You cannot simply just say, hey, it's 36. 36 what? What's the unit? Is it shrinking? Okay, don't assume everything is just, it's trivial. You should expect that nobody knows what you're doing. They are your client. They come to you and say, I have this problem. Can you do it? And then you need to end up writing a report explaining what you did. Still okay? It's just like in our case, the report is just one sentence. But in general, you should get to know how to answer a scientific question to other clients without assuming they know what you're doing. Okay, that's a key skill to get, which we call scientific fact communication. You may even take a class on that, which they teach you nothing. So either way, get a hobby of doing things like this. Try to explain hard scientific fact to other people, to people who doesn't know what you're doing, because eventually that's going to become a sales skill. You become a good presenter. In order to present that, you need to understand all the mechanics of the scientific process. So in a problem like this, in the exam, I will actively look for these four things. If you just go ahead and do it without assigning which rates, I'm going to minus your score. If you finish, you don't answer the question in words, I will minus your score. Okay, you may think it's a pain in the butt, but really, you're getting trained to write things in a really nice professional way. And plus, I mean, it makes your life easier too. All right, let's just try to solve another example together. This time, we are going to have a letter leaning against the wall. And the letter has a length, fixed length, 10 feet. Okay. This one is going to slide down if you leave it that way. Okay. How does this slide down? Well, the top slide downwards. Meanwhile, the bottom slide to the right. That's how the whole thing slide down, but it's still against the wall. Sounds good? All right. Now let's assume I measured the speed. This one is sliding away. It's sliding away at 1 feet per second. Now my question is, how fast is this one sliding downwards? If I know the bottom is sliding away at 1 feet per second, when this is 6 and this is 8 in terms of length. Is the question clear? All right. Before we do it, let's make a guess. I think everybody knows if this is 45 degree, which means this is a 4, this is a 4, they are the same length. Then if this one slide at 1, this one definitely slide downwards like 1 because they have exactly the same rate. Okay. Now we don't have it. We know this is shorter and this is longer. Still okay? So question, do you think it's going to be slower than 1? The red one? Or do you think it's going to be faster than 1? Knowing this is 1. Okay. Let's take a poll. Answer yes if you think it's slower. Answer no if you think it should be faster. According to your experience. One person thinks it's going to be slower than 1. The majority think it's faster than 1. Well, basically your answer is whoever has a longer length should slide faster. Sounds good? Now let's do the computation and see if we're right. Let me just keep the numbers here. You think about, you remember what you selected. Okay, see if your intuition works. First, set up 2 rates. One is the changing rate of what? Of how long this is. So I'm going to say this is X. I'm going to say this is Y. Then it's clear. dx over dt is the thing I know, which is positive 1. X is increasing. I want dy over dt. It should be negative, right? Okay, partial credits already. Number 2, you don't know the relationship between dx over dt and dy over dt. Then, do you know a relationship between x and y? Can you find an equation that x and y need to satisfy? Can you say it's going to be Pythagorean theorem because you keep attached to the wall and your letter doesn't change the size? It's still 10. So no matter how you slide, x may be longer, y may be shorter, but eventually this has to be true. Once you have that, the rest is mechanics. Take the derivative. Okay. Now what is your x? Your x is 6, as we pointed out. What is your dx over dt? That's going to be 1 plus y. 8. Don't know. Then dy over dt is going to be 12 divided by 16 negative, which is negative 3 over 4, which is less than 1. Slower. So whoever selected slower, you're right. The majority, you're wrong. Finally, the answer. The top of the letter is sliding downwards at 3 over 4 feet per second, and I'm actively looking for the units, and you need to tell me it's downwards. That's what this negative means. Your y is decreasing. That means downwards. Sounds good? Common sense, think about it. If you have something sliding down, does it start slow and then gradually really fast? Or does it start really fast and gradually become slower? Which way? Slow first, fast later. That's why this is going to be slower than 1. And once you pass the 45 degree, you're going to get faster, but this one's going to get slower. Sounds good? Okay, so actually, if you are actually before this stage, you are going to be slow. After this stage, you're going to be fast in terms of like dropping down. That's why whenever a letter slides down the ground, you feel scared because you know the sound is going to be really, really loud because the final velocity is really fast. If that thing actually go really fast at first and then slow down as time goes by, you don't have to worry about anything because that thing is going to be super, super gentle in the end. But sadly, that's not the case. Okay. Are we good with everything we have here for this problem? Okay. This is what we will do for the rest because there's nothing more to talk about other than giving you more examples. I would say, number 1, go to the web work. Try something yourself. If you feel like you need more, go to the textbook problems. On Monday's class, however, we will be together and finishing a worksheet on related rates. Usually I do group work, but since we're in pandemic, we just do it individually. So you come here, do it in class, and I will be monitoring and answering all the questions you have. Sounds good? To find the worksheet, you just, not this one. To find a worksheet, you just go to Canvas. And you go to Calculus 1. And then you go to Related Rates, which is in the lecture notes, okay? Related Rates. And you will have the whole sheet here, which has 4 problems. So that will be what we will be doing in class on Monday. Sounds good? Cool. That's all for today. If you want, you can start early and bring your questions on Monday. Otherwise, you can start on Monday too.